All right, so I'm going to talk about point proofs, which is a name we gave to aggregatable proofs for multiple vector commitments. And I'll try to define all these terms as I go along. This is work that was done at Algorand, jointly with Sergei Gorbunov, Hotek Wei, and Zhenfei Zhang. I'm Leo Reyzin, and people have since scattered to various other corners of the globe, but I'm still at Algorand. So there we go. All right. Let's consider a scenario that's hopefully comfortable for most of us. We have Alice, who has a message M, and she hashes it and gives a short hash of the message to Bob. And we can view that as a commitment to this message, in the sense that later, when Alice wants to reveal the message, she sends it to Bob, and he can just check that the hash of the message is equal to H. And so Alice did not change the message between the time when she first committed to it and the time when she revealed it. And this sense of the term commitment is not hiding. It's not designed to hide M, because, for example, exhaustively searchable, somebody could exhaustive search for M. It's just designed to bind Alice to M. So it's binding but not hiding in the crypto terminology. These are the kinds of commitments I'm going to be talking about. Okay. So that's a simple one message commitment that we just saw. Now let's talk about vector commitments. They were formally introduced by Catalano and Fiori in 2013, although they existed before in various forms, but their definition, they're the ones to first sort of name them. And the idea is that Alice should now be able to commit to n values, not just one, with a single short commitment, which we're going to call C. And then she should be able to reveal just one element, let's say the ith element, and a short proof that the ith element is correct. And Bob should be able to verify against the initial commitment, given the index I and the message mi and the proof. And an important feature of this vector commitment, as opposed to the single commitment we saw before using a hash function, is that Alice doesn't need to reveal everything. Right, this considerably saves bandwidth, because she can just reveal one element of the vector.
Leo, I think we may have a question. Someone raised their hand here. I'm not sure if they meant to, but let me just see if I can pull them into the chat. And if they have a question, I'll let them ask. If it disappears in 5 seconds, then we'll know it was potentially a misfire. But
yeah, sounds good.
We'll give it. And yeah, just a quick reminder for folks: only press your share audio video if you want to ask a question here. And you can do that, and that's no problem. Or you can drop the question into the chat. Great. Okay, I think it must have been a mistake. So Leo, why don't you go ahead and continue?
Sounds good. So there's a well-known solution to this problem of revealing just one element, and that's Merkle trees. They are based on hashing, just like the previous commitments, but they put hashing in a tree, essentially a binary tree where the leaves are the messages mi, and then you hash it in pairs all the way up to the root. And the only problem from our point of view is that the proof size is fairly big. The proof in this case for a Merkle tree is going to be the authenticating path, all the hash values on the way from the leaf to the root, which is 32 log n bytes. And what's log n? Well, log n sort of is always somewhere between 10 and 40 in real life. So we're looking at something like a kilobyte. Okay, so now what we want to do is have vector commitments with short proofs. And the way we can accomplish that is by a technique of Libert and Jung, which I will share in a little bit once we get to the technical details. It's based on pairings over elliptic curves. The proof size is just one elliptic curve point, which is 48 bytes for the kinds of curves we need to use there. And that is regardless of n, so it doesn't grow with n, unlike Merkle trees. And 48 bytes is much smaller than even the smallest Merkle trees will give you. The caveat is that you need public parameters, which consist of 3 n elliptic curve points. But once you have those public parameters, they're fixed and sort of hardwired, then the proofs are very short. And what about if I want to have short proofs for several elements? What if Alice wants to reveal not just one element of her vector, but let's say k elements? So at k indices I1 through ik, elements mi1 through mik, and one single proof for all of them. So she wants to reveal a subvector. So then Bob would know the subset, right? And for conciseness of terminology, I'm going to call the subset S. And that way I can have, S is my set of vectors, M sub S is the subvector. And I want a single short proof pi sub S. And I want Bob to be able to verify all of that. There is a way to do that, and specifically subvector commitments of Lia Malavolta from just a year ago, also based on pairings over elliptic curves, give us a proof size of one elliptic curve point, again 48 bytes, regardless of the size of the original vector and regardless of the subvector size. However, the public parameters grow where they were linear in the Libertarian vector commitment. They're now n squared, which is a bit of a problem, right? Because n squared elliptic curve points, if your vectors are of length 1,000, then that's like 1,000,000 elliptic curve points in public parameters, and that's a bit big. Okay, so let me get to now our goals of the work that I'm presenting. The goal number one is proof aggregation. So what's proof aggregation? If Alice commits to a bunch of elements, I want her to be able to reveal a few elements with their individual proofs. So maybe she reveals element I1 with its proof and element I2 and so on up to IK with their proofs. They each have a proof, but I want somebody to then be able to compute a single proof for this entire subset, SI1, SIK, and aggregate these individual proofs into a single subset proof. And then forward this on to Bob, and Bob should be able to verify, just like Bob did in the original, in the previous slide, subvector commitments, a single proof for this entire subvector S. And why might I want to do that? Because maybe Alice is a distributed system. She's revealing these proofs to different people at different times, right? She's maybe submitting transactions to a blockchain from different places. It's not actually a single Alice. And then I want to be able to aggregate these in order to save on bandwidth somewhere. So our first contribution is that we actually are able to do that based on pairings in the random oracle model. Our proof size is one elliptic curve point again, 48 bytes, regardless of n and k. So unlike prior work, we can not only have a proof for a subvector, but we can have an aggregation of individual proofs into a single proof from a subvector by anybody. And that person doesn't have to know the vector. And we have a short public parameter, so we went back from the n squared of Lia Malavolta to just 3n elliptic curve points. Okay, so that's our first goal. Our second goal is more ambitious. What we want to be able to do is imagine that we have a bunch of Alices, Alice 1 through Alice L, and each of them will commit to a vector of her own. So M1, Mn, Mn all the way right through Ml. And now Bob has a bunch of these commitments. And these various Alices will reveal some subvectors and their proofs, right? So the first Alice might reveal a subvector 1 with its proof. That itself, the proof could have been computed in an aggregated way using the sort of what I presented on the previous slide. And the second Alice might reveal her own subset and so on. And then what I want to be able to do is to, again, for anybody to aggregate these subvectors into a single proof that can then be given to Bob. So Bob is going to be given the subsets and the elements of these indices, which is sort of necessary. That's the information he actually wants, plus one single short proof, and he should be able to verify all of that. So cross-commitment proof aggregation has not been done before. We actually define and achieve the first cross-commitment proof aggregation, where again, the proof size is just 48 bytes, which is one elliptic curve point, regardless of L and N and subset sizes. So regardless of how many Alices you have, how long the vectors are, and how long the subsets they reveal. And our public parameters are going to stay at, again, 3n elliptic curve points.
Leo, just wanted to stop you here quickly. There is one question in the chat that Aline, I think, took a stab at answering, but just wanted to flag for you. And the question is, what is the cost of aggregation?
Yeah.
Go ahead.
Aline, thank you for answering. You answered correctly. So the cost of aggregation, and I'm going to show how it's done and talk about it in more detail, but for each thing you're aggregating, you are going to pay one elliptic curve exponentiation or scalar multiplication, depending on how you prefer your elliptic curves to be named.
Great.
All right, so good. The crypto assumptions that we need are the random oracle model and pairings. And specifically on the pairing side, we need something called weak bilinear Diffie-Hellman exponent assumption and the algebraic group model, which sort of models the pairings as somewhat idealized primitives. Okay, so now that I've told you what it is we've done, you may ask how we do it and why we care. Let me do the how first and then come back to the why. Okay, so the how, I need to give you a bit of background on bilinear pairings, and then that will hopefully help understand how we actually do it. So here's how we're going to view bilinear pairings. We're going to think of a group generated by some generator G, where the discrete log is hard. We're going to call that a source group. And because writing things in exponential notation is a pain, and G is always going to be our generator, instead of G to the X, we will write curly braces X in red. So it's both red and curly braces, just so you can see it in case color is not coming through or you're colorblind. Okay, here's an important thing about exponentiation. Given n and x in curly braces, we can compute n times x, right? That's just raising G to the X to the power n. And also given x and y, which are actually G to the X and G to the Y, right? We can compute x plus y. That's just group multiplication. So keep that in mind, that given n in plane, not in curly braces, actual n, and x as G to the X, we can compute these things. Okay, the second part of our setup is that we need a different group, again, of the same size. It's called a target group. It's going to be generated by something called GT, a different generator in a different group. And discrete log is also going to be hard in that group. And in that group, instead of using curly braces in red, we're going to use square brackets in blue. But the group by itself behaves the same way. The same computations are possible. Given n and x, you can get nx. Given x and y in blue brackets, you can compute x plus y. And the third ingredient that connects these groups is a bilinear map that takes x and y in the source groups and gives their product in the target group. So it sort of it computes Diffie-Hellman for you, x times y, right, which is a magical thing that should be hard, but it doesn't quite do that. It moves things to a new group. So this bilinear map only works for two red elements to give you one cyan element, and any kind of inverse is hard. It's not that you can go back and then move x, y into the red curly braces and then do one more to get x, y, z. It doesn't work like that. This is sort of a one-time thing. Once you've moved from red to cyan, you stay there. For those who are a bit more familiar with this, the connoisseurs of bilinear pairings will know that actually often two source groups that are slightly different, but for simplicity, we will stick with one source group here. So there's one source group and one target group. In reality, there's actually a left source group and a right source group, but that's not relevant for the purposes of this talk. Okay, so that's the background. And now I'm going to tell you how commitments from Libert and Jung work. There's something interesting about our work. What we actually were able to do, and what we only realized after sort of doing the work and reinventing the commitments, is take the commitments of Libert and Jung and make them aggregatable. So Libert and Jung commitments are from about 2010. I forgot to put the date on the slide. Here's their trusted setup. The trusted setup, remember I told you it was going to be a linear number of elliptic curve points. The trusted setup needs the following points. It needs, in the red group, the curly braces group, it needs a squared, a cubed, a to the n, all the way to a to the power 2n. N is the length of our vector here. So we need double the length of our vector. But we do not need, in fact, we should not have element a to the n plus 1. Okay, remember again, these aren't curly braces, so it's not like given a, you can compute a squared. This is g to the power a, and g to the power a squared, and g to the power a cubed, and so on. And so a to the n plus 1 is not there. But a to the n plus 1 is only available in the target group in the blue brackets. Okay, so let me cross it out just as a reminder that it is not there, and nobody should know it. And this setup has to be trusted. If somebody screws it up, we're in trouble. Fortunately, it's a relatively easy, actually quite easy MPC, multi-party computation, that can give us the setup where you need a random A. And basically, you can have a multi-party computation where each party comes and modifies the previous party's result by re-randomizing it with its own random A. And then in the end, you will end up with a product of all the A's. So it's a sort of a non-interactive multi-party computation. Anybody can come and modify the previous result and add their own randomness. It's a bit like sort of collecting a randomness for uniform random strings. And you can prove that you actually modified it correctly without too much trouble using Bilinear pairings. So the setup is not too bad. Once you have this setup, okay, oh, sorry, this is an important thing, that our assumption implies that a to the n plus 1, that missing element in the source group, is hard to find given everything else. You have it in the target group, but you can't have it in the source group. Okay, so once you have this setup, you can ask, all right, how do we commit? And the way we commit is we have, again, a vector of length n, right? And we want to output a commitment C. We're going to take the following result. We're going to multiply A by M1. Remember, M1 is M1 is in the clear. It's not in any group. So we can multiply M1, A by M1, and then we can multiply A squared by M2 and A cubed by M3, and so on. And then we can add them all up because we know how to add red elements. And that's going to be our commitment. So one way to think of this commitment is that it's essentially a dot product of two vectors. It's a dot product of the M vector and the A vector. And the reason we're able to compute this dot product, even though the A vector is in the exponent, it's not actually known to us. It's g to the A vector, right? Is because the M vector is known. So the M vector is known, and that's what enables us to compute the dot product. And that's our commitment. Then how, not actually our commitment, that's a Libertarian commitment. How does one then prove an element of this vector? So to prove M1, here's the proof I'm going to do. I'm going to, there's a deliberately crossed out element. I'm going to imagine that I multiplied M1 by A to the n plus 1, but of course I can't. I don't have A to the n plus 1. Nobody has it. And then I'm going to multiply M2 by A to the n plus 2, M3 by A to the n plus 3. The sort of the tail end of the red vector is going to get multiplied by the original vector, except the M1. I'm proving that M1 has some value. I don't actually need to include M1 in my proof. I need to include all the other elements in my proof. And the way I include them is by multiplying them by the tail end of this vector. And this multiplication essentially places M1 into the one missing position. So the way to view it pictorially is that I again did a dot product of the M vector with now the tail of my public parameters, except the missing element of the M vector I did not use. Okay, so that's how I'm going to come up with a proof for M1. What about a proof for M2? The proof for M2 is very similar, except I'm going to shift, there's an error on the slide, best fixed in real time because it's going to be very confusing. Voila. Okay, there we go. The way I improve M2 is I shift the vector 1 to the left. And now M2 is in the missing position, right? M2 is in the position where I don't have the public parameter A to the n plus 1. And I again do a dot product of the M vector with the A vector, that piece of the A vector that I'm currently using. So that's going to be the proof of M2. And the proof of M3 is going to be, again, a one shift of the M vector. So the proof of M3 is a dot product of the M vector with a portion of the A vector. Which portion? The portion that makes sure that the thing I'm proving is actually in the gap in the public parameters. Okay, so the proof for each element consists of a dot product of all the other elements with a relevant portion of the public parameters vector. Okay, so these are all the proofs. Eventually, if you go all the way to the left, right, for proving the nth element, it's going to be a dot product with again almost the leftmost portion of the public parameters. So proving and committing look very similar. And sort of previewing, once we're going to start talking about the cost, you can see that both proving and committing takes a linear number of elliptic curve operations in the length of the vector. Okay, so generically, if you want to prove MI, you put the ith element under the hole in the public parameters, and then you dot product the rest. Okay, so now given that this is the way you prove things, how do you verify things? What does the verifier have? Let's think about it carefully. The verifier has the commitment, which is an element in the source group, the index and the value that is being proven, and the proof. Okay. So here are the things the verifier is going to do. The verifier is going to first move the proof over to the target group, which is where the bilinear pairing operation comes in. Because remember, the pairing operation, as it takes two red elements, it'll multiply them together to give us a blue element. So I'll just multiply pi I by 1 to give pi I in the target group. And then, and this is the more interesting pairing operation, we're going to multiply our commitment by a to the n plus 1 minus I. If you think about what that does, it'll shift the commitment to the right, exactly to where the proof was. It'll shift the commitment to make it so that the element we're proving, the ith element, sits right under a to the n plus 1, right? Because a to the n plus 1 minus I plus I is being the ith element, is a to the n plus 1. That's the missing piece. Okay, and the verification equation, then after I've done these two shifts, is simply to check that the proof is equal to this shifted commitment. Okay, the shifted commitment is just a shift of the dot product vector I places to the right. But the proof does not have one thing. What does the proof not have? The proof doesn't have the ith element multiplied by a to the a plus 1. So I'm going to subtract it. How can I subtract it as a verifier? I don't have a to the a plus 1 in the red. I have it in the blue, which is exactly what enables me to subtract it. Because having a to the n plus 1 in the blue is enough to be able to do operations in the target group. So that's the entire verification thing. It's two pairings, and then we have to do a comparison, which is nothing. Okay, so there's Libertarian commitments invented about 10 years ago, and they're actually quite simple, right? It's dot products to commit, dot product to prove, and to verify, you shift things to the target group, and you shift the commitment over to the right to look like the proof. And then you may ask, okay, well, why is this secure? Like, it works, but why is this secure? Here's security intuition. Imagine that I wanted to change MI. I wanted to lie about what MI is. Okay, if I want to lie about what MI is, this equation needs to work. How is this equation going to work? Okay, what are my choices as the adversary? What can I mess with? Well, I can't mess with C. The commitment has been committed. I can't mess with a to the n plus 1 minus I or a to the n plus 1. Those are in the public parameters. The only thing I can mess with is the proof in this equation, right? The pi I on the left. Okay, well, how can I mess with pi I? I need to add, pi I is given to me in the red. It's not given to me in the blue. I need to give it to the verifier in the red. If I'm the adversary, I need to give the verifier a red pi I, because the verifier is going to move it over to the blue group. So if I give the verifier a red pi I, it better have an appropriate change to it so the verification equation is going to hold. But what change? The change has to be in the coordinate that corresponds to the missing a to the n plus 1 red element. But I don't know that element. It's missing. In fact, the assumption is that it's hard to compute. So there's no way for me to change MI and add the appropriate multiple of a to the n plus 1, because I would have to know what I'm adding, because I would, I'd have the old pi I and the new pi I prime. So that's the intuition behind why this commitment is secure. Obviously, there's a whole proof behind it, but the proof roughly follows this intuition. So now we come to our technique. Thanks for bearing with me for the background. The technique for same commitment aggregation. Okay. I want to aggregate, let's just do two proofs. I want to have a proof for pi I, and I have a proof for pi j. So I have a proof for the ith element, the jth element. I want to aggregate them. What I'm going to do is choose random, and random is in quotes because we'll have to think about how to choose them in a minute, ti and tj, and just do a linear combination of the two proofs with random coefficients, ti pi I plus tj pi j. And that's going to be the proof for the two elements I and j. And this generalizes in the most obvious way for 3 elements, 4 elements, and so on. You're just going to choose random coefficients for each of the proofs, and you're going to do a linear combination of the proofs with these random coefficients. And the reason you can do that is, again, because we can multiply in the red group by black elements, and then add things. Okay, let me show you why this works, or what sort of happens. What is it that I'm doing? I'm multiplying pi I by ti. Let's just write the verification equation multiplied through by ti. It's just like the original equation on the left, the blue equation that you see, except now it's all multiplied through by ti. If the equation was false before, it's still going to be false, unless ti is 0, right? So the verifier can totally multiply things by ti and not hurt security. And if it was true before, it's also going to be true before. Multiplying an equation by ti does no harm and no good. Multiplying the second equation by tj will be the same. So if the equations were true before, they're true now. And essentially what happens is now I'm adding the two equations because I have ti pi I and tj pi j. Here's a nice fact. If you had two equations that you wanted to verify, and you want to verify just one because you're lazy, all you need to do is multiply equations by random numbers and then add them up. If the original was true, the result is still going to be true. If either of the original equations were false, or if both were false, then the new thing is false with overwhelming probability. The only way if the equations were false, the new thing becomes true is if you're very unlucky in your choice of ti and tj and things cancel out. But if they're random, that's not going to happen. So if you think of the new verification equation, it is pi ij on the left, which is just a linear combination of pi and pi j, and then the appropriate linear combination of the things on the right using distributive law. There's nothing interesting going on here. The verifier can still do this verification by just using the TIs and TJs and appropriately modifying the verification equation. And again, if you have more than 2, you do the same thing. Okay. So to verify many proofs at once, again, let me summarize this in words. We're going to take a random linear combination of the verification equations. And if at least one equation fails, then the combined one will fail also with high probability. And then you may ask, okay, but where do these random TIs and TJs come from? There's an aggregator who aggregates. There's a verifier who checks. Obviously, we can't trust the aggregator to check the pick TIs and TJs, because then the aggregator could pick ones that will make 2 false equations into a true one by lucky cancellation. So the technique is pretty standard, actually. The way we're going to choose random values that the verifier needs and the prover has to come up with is by the Fiat-Shamir technique, which is to hash the statement that is being proven. If you hash the statement that's being proven, then the prover has no chance of messing with the randomness, and the verifier can be assured that it was well chosen as long as the hash function behaves well like a random oracle. So what do we need to hash in this case? We need to hash the commitment, the indices I and j, and the messages mi and mj. And if there's more of them, then you hash the entire subset, right, and the indices that correspond to that subset. And so that's how you pick the coefficients. That's the entire, actually, let me go back for a sec. That is the entire idea behind same commitment aggregation. The rest is working out the efficiency and making sure you can do this verification efficiently. And the cross-commitment aggregation, remember the second part of the work, which is we can aggregate the same way for many commitments, uses the exact same idea. It's random. It's a random linear combination of proofs and of verification equations. And I will not bore you with the details because the math gets more hairy. There are now more commitments lying around, but the actual technique is the same. You take a random linear combination of verification equations and you get the aggregated proofs. And the nice thing is that we were aggregating, 48-byte proofs, but we're aggregating them into now a single 48-byte value, no matter how many of them there are. Okay, so that's the aggregation technique. I want to focus on one other useful feature of Libertarian commitments, and that is their updatability. Remember, that's our commit equation. M1 through Mn gets committed by this dot product, M1a plus M2a squared, so on. Imagine that M4 changes to M4 prime. I want to update the commitment without recomputing everything. And turns out that's very easy, right? Because if you think about what changes in this vector, the dot product, C will change to C prime by just a small change. I need to add M prime 4 a to the fourth and subtract M4 a to the fourth. So I can update the commitment with knowing just the old value and the new value. I don't need to know all the other M values. And that's going to be a useful feature in the next step that I described. So remember this, we can always update commitments by just knowing the old value and the new value that changed. And actually the same for proofs. Proofs are just dot products, and the same exact idea applies. Okay, so you can run update without knowing the other values. Okay, so now that I've told you how we do cross-commitment proof aggregation, you may ask, why do we care? And so let me give you two applications, one in a bit more detail than the other, of why we do it. Okay, so obviously you want to do it when you collect proofs from multiple sources. And the first use case we explore in the paper is, imagine that you have smart contracts with large memory state. So you have a smart contract owner, and the smart contract maybe has many variables, so memory is big. And the owner of the smart contract will commit to the entire current state of the memory, initial state of the memory, let's say. And this commitment will be known to the cryptocurrency validators, who will not need to know the entire memory state of the smart contract, right? And it'll be one commitment per smart contract. So what we're doing is we're replacing the large state of the contract with a small commitment to the state. Now, a transaction, which is a call to a smart contract, may touch only a few variables in this large memory, right? Maybe you're updating only a little bit. Okay, so let's say that there are users who submit transactions and to many different smart contracts. In each transaction that gets submitted, we will submit the transaction and the variables that were touched, only those that are touched by this transaction, and the proofs. And then a block proposer will be able to perform the transactions because the variables that are touched by a smart contract call are known as part of the transaction, and aggregate all the proofs together, and then send all the transactions on all the variables touched and a single proof for all of it to the validators, who will verify and update every commitment, because remember, commitments are updatable as part of the transaction call. They'll be able to see how to update the commitment, which variables changed. And so what we did in this example is we traded memory state for bandwidth, because now the validators don't need to have the memory state of every smart contract. They need to know only what a particular transaction touched, and they will be able to verify and update every one of them. But as the trade-off, they need to now find out what variables got touched. Fortunately, they do not need to waste any space on proofs, because a single aggregated proof of just 48 bytes will cover everything, every smart contract and every variable touched. So this approach makes sense. Yeah.
Sorry, Leo. Yeah, just to call. There's a discussion that's kind of going on in the chat right now around.
Oh, let me read it.
Yeah, go ahead and take a look.
I was reading up the paper some months ago, and as far as I know, there's a limitation on the I size. Okay. Oh, sorry. Alan is responding. Thank you, Alan. There is an upper bound on the size of the vector being committed to. Indeed. Verification time grows with L. Indeed. So Robert's question is verification time. This is not L. This is not I. This is L. Right. Thank you, Robert, for clarifying. All right. Let me explain for those who are not following the discussion. If you have many commitments, then verification time will grow with the number of commitments. Indeed. The size of the proof will not, but the verification time will. And that's a drawback, but note that everybody has to do work linear in the number of commitments currently active anyway, because you're going to have to run every smart contract that is being invoked. So if L is the number of smart contracts that got run, then every smart contract has to do something. And yes, you also need to validate the decommitment for every one of them. By the way, the cost of this verification is one pairing per smart contract or per commitment, which is the same thing in this example, but only for the ones that are touched in this particular block. So smart contracts that are dormant and not being invoked do not contribute to your cost at the moment. Okay, yeah. Robert's second question is whether we can use this for the whole blockchain state and not a single account, and it seems it will not be practical for that. Imagine millions of accounts. So again, millions of accounts are not a problem. It's the thousands of accounts that are in a particular block that we need to think about, because accounts that are not touched in a given block do not contribute to your verification time. There are other barriers to using these vector commitments as is for the whole blockchain state, because the vector length is where you run into trouble. N is the size of your public parameters, the size of your vector, and the verification, and the constraint on generating proofs. And there, using a single vector of length 1 million is going to be a problem. Fortunately, we have follow-up work that I'm actually going to talk about in about 2 minutes that figures out how to use these for the whole blockchain state. So Robert, hang on, and I think I will answer your question to some extent, and then maybe we'll follow up. I'll explain how we commit to the whole blockchain state.
Okay. Cool. And we've got a few more questions. How about maybe we'll let you get through your next segment. So I think we've opened up the floodgates now that you started answering some questions there. So maybe why don't you, I suggest this, since we have 20 minutes left, go through your next segment that you have prepared. And then when we have time at the end, we'll aggregate all the rest of the questions. Does that sound okay to you?
Yes, aggregate was a good pun. Nice job. Let me just, the other questions are actually quick. Can we consider Libertarian as a type of multi-trapdoor Mercurial commitment? I think, in fact, that's what it is, but it's not particularly relevant for what we're doing with it. But there's some work on that. And then Sanaz is asking, do the validators have to know the public parameters of each smart contract? So to answer Sanaz's question, there is one set of public parameters for everything in the entire world. It's sort of in your code base, nobody needs to generate it again. So it's one set of public parameters. You can use many commitments for public parameters. So it's just, 1,000 values, for example. That's not a big deal. Robert, I'm going to get back to your question, and you can ask it again if I haven't answered it. Okay. So actually, let me talk about the second way to use cross-commitment proof aggregation. I talked about the smart contracts use case. Now let's think about stateless validation, not just for smart contracts, but maybe for the entire cryptocurrency state. Since I'm getting close to time, and this is an entire separate piece of work, I'm going to refer you for a lot of details to a paper called Aardvark, and I'll have a link at the end. Joint work with Derek Lung, Yossi Gilad, Sergey Gorbanov again, and Nikolai Zeldovich, where we talk about how to apply vector commitments to account-based cryptocurrencies. But let me give you sort of the very high-level view of what we do. Imagine that you have all the pairs of public keys and balances, everything in millions of accounts, right? And you want to commit to them all and put this commitment in the block header. And the basic transaction, let's just think of a simple transaction. It requires you to update balances for the public key of the sender and the public key of the receiver, right? And so again, we can say that the users will submit the transactions, the balances that are touched, 2 per transaction, the sender and the receiver, and the proofs. And the block proposer will aggregate all the transactions, all the balances touched, a single proof now. So we save on the proofs, it's just 148 byte thing, and the new commitment C prime, which will go into the new block header. And the verifiers should be able to verify, update C, and check if the result is C prime. That's pretty straightforward. Here are the challenges that I'm not going to discuss unless some questions come up, but I don't have any slides planned for a lack of time. We have, what I've presented so far is a limited length vector, like a vector of length 1,000 or maybe 10,000, whatever public parameters allow you to do. And this vector is an array, right? You can index into the ith element. But what I want to do is actually have an associative dictionary. I don't want an array. I want to be able to go from a public key to a value. That's an associative array, right? And vector commitments by themselves don't give that functionality. The other challenge that happens with a large-scale deployment is that now you have asynchronous transactions, right? Because they come in out of order. So the proof that I give for a transaction at the time I create it is stale. It's out of date by the time the transaction gets processed, potentially. And so the validators cannot validate it with respect to the most recent C prime because C prime got updated. Now, we know we can update proofs, but that's expensive. We don't want everybody to be updating every proof all the time. So to handle asynchrony, where the proofs go out of date and the validators need to update things in an asynchronous order, and to convert from arrays to dictionaries, we actually have a separate paper called Aardvark that handles these challenges, that essentially generates an associative array out of a set of small 1,000-length non-associative arrays by storing some extra tables, storing next pointers in the array so you can know what's missing, what's in the gaps, so you can know exactly which accounts are missing, and by careful handling of these asynchronous processes. That paper is on ePrint, and the link is 2020-975. I can put it in the chat as well. So that's all the detail I want to go into for now, but I'll be happy to take more questions. Let me tell you a little bit about performance of these things. And this performance numbers are, I'm presenting performance numbers that are from a year ago. We have not updated the benchmarks with the more efficient implementations of pairing, so they should improve with better pairing libraries out there that have been produced since then. A single commitment proof is essentially a single multi-exponentiation. So for vector length of 1,000, that's a 1,000 long multi-exponentiation that takes about 70 milliseconds. A cross-commitment aggregate is one multi-exponentiation that the size of this multi-exponentiation is as big as the number of commitments you're aggregating. And so that's very quick per commitment. That's only 0.07 milliseconds, so 70 microseconds per commitment. So aggregation is fast. And the verification cost, the way to think about it is it's one elliptic curve exponentiation per message and one pairing operation per commitment. And so let's say this, now you have to, it's a linear combination of two things, so you have to be careful with your parameters. Let's say you have 8 messages that you revealed per commitment, as in the smart contract example, maybe there are 8 variables that got touched by a smart contract call, then the cost is going to be 0.7 milliseconds per message. And as I said, these numbers can be improved with better curve implementation, but that's the rough ballpark, so you get an idea. All right, let me conclude and then get to more questions if there are any. What our paper does is it gives you the shortest proofs in same commitment aggregation. Same commitment aggregation existed before us, but the proofs were considerably longer. The first ever cross-commitment aggregation, and the proofs are again very short, 48 bytes. We have a cryptocurrency smart contract application, and there is an implementation available on GitHub under Algorand Pointproofs. And I think that's it. I'm happy to take more questions.
Great. So yeah, anyone who has questions, feel free and raise your hand and or post in the chat. And then I guess maybe Leo, if you want, the conversation is sort of ongoing. So maybe if you can restate the benefit of this approach versus traditional approach in a cryptocurrency setting. Oh, it looks like Aline is going to stand up and elucidate and or ask a question, but maybe Aline, just hold one second. Leo, why don't you go ahead? Go ahead.
I think, Alex, thank you. I think it's a good idea to let Aline answer. Let me just say one thing. Robert was asking, if you have 100 billion accounts, then you need to recurse 3 times for aggregation of aggregations. That is indeed one way to do things, is to have a tree, essentially, of vector commitments. Another way is to realize that you can do quite well by just dividing things by 1,000 and not recursing. And so a set of 1,000 a set of vectors that is 1,000 times shorter than the number of accounts is actually pretty good already, and you don't necessarily need to recurse any further. Or if you feel like it, you can put Merkle trees on top and so on. But once you've reduced things by a factor of 1,000, you're doing pretty well already. But Aline wanted to speak, so I'm happy to let him.
All right, let me bring Aline up here. Let's see if this works.
Oh, wow.
Perfect.
Hi, Aline.
Welcome to our session.
Thanks for the talk, Leo. It was really great, really fantastic presentation.
Thank you.
I was wondering, I just really wanted to follow up on an earlier chain of emails regarding pre-computing all proofs efficiently in this construction. I was wondering if, I was wondering if you've thought about whether that's possible at all, or whether it's actually inherently difficult to do because of the LY structure and these dot products which have to be shifted.
Okay, so you're asking a very good question, and I think there has been some work on, I think it's in the context of a different set of vector commitments, the Bonnet, Bunz, and Fish vector commitments, where they are pre-computing all the proofs at once with some pretty clever FFT-like tricks. But
the KZG stuff, or the because Bonnet, Bunz, Fish is just accumulators, so they do.
Okay, so I'll probably screw up the answer right now in real time. I remember seeing some work on pre-computing all of them, but I don't remember the context, and it wasn't the same thing as what we were doing. So the answer is I'm not sure. A second answer, maybe a slightly better answer, is that a lot of the techniques that I presented here are also applicable to what are known as polynomial commitments, where you commit to P of X and then a reveal is a valuation of a polynomial on a given point. And you can see that because, right, our exponents are essentially a polynomial, monomials, AA squared, and so on. And so there's a pretty tight relationship between vector commitments and polynomial commitments, and people have looked at efficient vector commitment pre-computation of proofs for polynomial commitments, and some of the same techniques may well apply. But I have not. I'm not willing to sort of figure this out in real time, probably. But it's a good question, and we have. So in an appendix of our paper, we actually show kind of the polynomial commitment view of the same thing.
Right.
We translate some of the aggregation. So I think the answer is that I wouldn't be surprised if something is possible, but I have not looked at it myself.
Yes.
That's probably.
Yes, I like the idea of trying to apply the Feist-Kovratovic technique for pre-computing polynomial proofs to this construction, which can be regarded as polynomial. That's interesting. Yeah. Okay, cool. Yeah, thanks so much, and thanks again for the talk.
Thanks, Aline, and thank you for not making me ask all that, repeat that from the chat. So it's much more efficient for you to just say all that.
Sure.
I'm gonna send you off now, but we'll get to a couple other questions here. Great, and so I guess maybe we'll take. So we have time, I think, for 3 more questions. We'll we've got 2 in the chat here. So Leo, maybe I'll let you read off of them if you see them, or I can read them. You tell me what you prefer.
Okay. Oh no, I can read them. So is Aardvark going to build authenticated dictionaries on Algorand as layer 1 or layer 2 smart assets? And the answer is that we haven't yet announced how we're going to use authenticated dictionaries. This is for now a research project, a paper and code. There's no strategy announced yet for how we're going to release them. And then Robert is asking, do you see it possible to extend the scheme for exclusion proof that a value does not exist in a commitment? So let me give 2 answers. If we're just talking about vector commitments as a pure primitive, then there's no such thing as an exclusion proof because it's an array of 1,000 elements. Arrays are initialized to something, so there's always something there. You can decide that it's something undefined, but it is something. There's no exclusion proof. However, if you're looking at a dictionary, public key to balance, let's say, or whatever, then of course you want to have exclusion proofs. You want to have a proof that something does not exist in your map. And the answer is that, yes, we do provide exclusion proofs. We provide them essentially in a dictionary application in Aardvark We provide them as exclusion proofs by essentially storing next pointers and showing that the correct next does not exist. And then the technically interesting piece is how do you update these next pointers efficiently when things change? So I'm posting into the chat the links to the paper itself and to point proofs, and I see that Alex already posted, and I'll repeat it here, the link to Aardvark, which is the system that builds on top.
Yeah, and just maybe clarifying, I think Robert's follow-up question was compare, so Merkle trees, you can show that something doesn't exist by showing two neighbors. So I guess is there an equivalent in this construction?
Right. So again, these constructions are not, in Merkle trees, you can show that something doesn't exist by showing two neighbors if you have alphabetized the Merkle tree. Typically, you don't alphabetize your array. Alphabetization is a good technique for static data structures. It is a terrible technique for dynamic ones. You don't want to do expensive insertions, right? What you do is you maintain a binary search tree or a trie or something like that. And you can build such things on top of vector commitments, indeed. And you do that is exactly by showing two neighbors. You basically show next pointers.
Great. So with that, I guess let's take one more question before we conclude. Does anyone else? I guess we'll leave 10 seconds or 15 seconds here, give some time for the lag. But if anyone else has any final questions, please either write them in the chat or raise your hand. And before we conclude here.
I have a question, Alex. What's happening during, is the break a break, or is there something happening on the stage or somewhere else? Or we log out and we log in again?
You're stealing my thunder for the after your talk. My talk.
I will let you do it on your own schedule.
But I think we might. It looks like I'm not sure if there's any other questions. So to answer your question, Leo, and for everyone's benefit here in the session, there is an activity plan for the break. We'll be meeting in gather.town. So for those of you who stuck around to the end yesterday, it's just kind of a virtual environment where we can socialize and do different stuff. We've got a lot of different activities that you can do in there. There's actually, there's a couple, I think the top left corner of the map, you can see the main stage talks replaying yesterday. There's some chessboards, poker tables, and if you see a little sprite sitting by itself playing Sudoku in the corner, rest assured that's me. But yeah, anyways, let me drop the link here in the chat now, but this is where we're kind of going to be hanging out in between, or yeah, for the break. And then, oh, perfect. Sean just dropped the link in there. Let me drop this one. Yep. Same link. And then there's a password. Let me drop that in here too, so you guys have it. And yeah, so this is where we're going to be during the break. And then please don't go away. That's the password I just posted there in the chat. Please don't go away before the end of the day, because we're going to be meeting back up and gather after the last talk, and we have kind of a special surprise plan. It'll be a new link, but yeah, stay tuned for that. You definitely won't want to miss it. So in the meantime, I guess thank you very much, Leo, for presenting this work. I think we all learned a lot, and there's a lot of interesting discussion here. Thank you to everyone in the session. And special thanks to you, Aline, for helping me moderate and answering questions in the chat. But yeah, thank you to everyone who attended, and I hope to see you all in the gather kind of space here. Thank you, Leo.
Thanks, Alex, and thanks everyone for coming, and thanks, Aline.